My way of understanding electromagnetism. I'm Per Wallander and I will talk about, well, NASA says, to be honest, we don't know what gravity is. We only know how it behaves. I will talk about gravity. I will talk about energy of movement. Where is that energy stored? I will give a more correct description of the capacitor. I will visualize Maxwell's equations. I will give a possible explanation to the double slit experiment. There are 4 different forces between particles. Are the forces really different, and where do the forces come from? Curved space. What is curved space? We will do some very simple measurements. This is my camera assistant. He keeps the camera in focus. We have a signal source, in this case a 144 megahertz amateur radio transmitter, and the signal goes through a very long cable that attenuates the signal 20 decibels, and then it's fed into a slotted line, a coaxial line with a slot in the screen, so we can measure the fields inside the cable. And at the output we can terminate the line with different loads. The output here from the transmitter is approximately 25 watts, and this signal from the transmitter is fed through the cable on the line and back to the transmitter. Because of this cable that attenuates the signal, we have 250 milliwatts into the line, and the maximum power that can be reflected is 250 milliwatts, which is 2.5 milliwatts when it reaches the transmitter, and this level is so low that it cannot affect the output of the transmitter, and when it's reflected out on the line, the forward signal is always kept constant, 250 milliwatts. So this coaxial cable that attenuates the signal is the secret behind my measurements. This is the transmitter. This is the coaxial cable that attenuates the signal, and this is the slotted line. The slot and the center conductor in the line. And over here the line is terminated in a 50 ohm resistor. This is a directional coupler, just a simple conductor terminated in a resistor, and if I insert it this way in the line, it senses the signal that goes forward. So if I start the transmitter, this is a voltage proportional to the forward signal on the line. And we see that this signal is constant along the line. It doesn't change in amplitude, and it's the same everywhere. Okay, what happens with the signal if I remove the 50 ohm load? Now I have removed the load. This is a short circuit, and I can connect the short circuit. And what happens to the forward signal? Nothing at all. I am measuring here 10 centimeters, 5 centimeters from the end of the cable, and this is a short, and now it's open, and now it's terminated in 50 ohm, and nothing happens to the signal going forward on the line, because this signal hasn't been here yet, so it doesn't know what's happening at the end of the line. But if I measure the reflected signal and remove the 50 ohm load, then of course I have a signal. And this signal is constant all along the line. We have forward power on the line, we have reflected power on the line, and these radiations are constant all along the line. I have changed to another oscilloscope that is a little noisy, but it works better with 2 channels. Now I have a probe, 2 probes. One probe is just a little pin to measure the electrical field in the line between the center conductor and the screen. The other one is a loop to measure the magnetic field circulating the center conductor. And I am also using the directional coupler to trigger the oscilloscope. So now I have terminated the line in 50 ohms, and I start the transmitter, and we can see the upper trace is the electrical field, the lower trace is the magnetic field, and the electrical field and the magnetic field are constant along the line, because we have only the line is terminated, so we have only forward power on the line. And we can see the traces are moving when I move the probe, because the triggering is fixed. Okay. Now, if I remove the termination, 2 things happens. The first thing is that the traces don't move sideways. They are fixed. This is a so-called standing wave, which is the interference between the forward power and the reflected power. And we can see that in the electric field there are points where the electric field is 0, and there are points where the electric field is maximum, and there are points where the magnetic field is 0, and points where the magnetic field is maximum. And this is interesting because in this point here we have only a magnetic field. No electric field, no visible electric field at all. But there are electrical fields because we have the fields from the forward power and the fields from the reflected power, but they are in opposite phase, so the sum is 0. And the same in this point. Here we have only a visible electric field, but no visible magnetic field. But still there are magnetic fields in this point. This is an electric field, E. This is a magnetic field, H. Then we have radiation, S. There is a right angle between the fields. And we have the well-known formula E cross H equals radiation S. They are vectors. Now, suppose another radiation is coming from this direction, like that. Now we have two electric fields adding to twice the amplitude. We have magnetic fields in opposite directions, and they are invisible. And radiation in that direction and radiation in that direction cancel. So for a mathematician, this is only an electric field. Now the question is, does radiation consist of electric and magnetic fields? Or does an electric field consist of two or more radiations in different directions, making the magnetic field invisible? We discovered fields before we discovered radiation. Does that mean that radiation consists of fields? Or is it the other way around, that a field consists of radiations? This is the question we will investigate in this video. Here we have two identical radiations, E field, H field, E field, H field, and they are traveling with the speed of radiation. And here in the middle we have where the electric fields are identical. We also have magnetic fields that are equal in strength and therefore invisible. So there we have a time-varying electric field. This is a time-varying electric field. And the magnetic field in this point here is invisible. But on both sides of this middle point, here we have electric field we have magnetic field in that direction, and here we have magnetic field in that direction, and that makes the field rotate around this point, rotating in such a way that it's pointing up in the same direction as the electric field, and that is, of course, the rotation of H. And this is a visualization of the famous formula rotation of H equals dd dt. Now we changed the polarization of the signals, and they are coming here, and in the middle we have a time varying magnetic field. As we have here. And there we see the electric fields in this point is invisible, but here we have an electric field in that direction, and there we have an electric field in that direction, and that is rotation downwards in the negative direction. And of course this is an example of the other of Maxwell's equations, that one with a negative sign for the magnetic field. This is radiation, the electric field, and this is the magnetic field moving in that direction. Now we have a value here which is changing in time, delta t, and the change in time is the same as the change in distance delta z, and they are connected being the speed of the signal, which is 1 divided by square root mu epsilon. Okay. And we have E is linked to H by the characteristic impedance, which is square root mu divided by epsilon. From these two equations we get that from this one, 1 divided by delta z equals square root mu epsilon times 1 divided by delta t. And here we have E equals H square root mu divided by epsilon. We combine these equations and get E divided by delta Z equals square root mu epsilon times square root mu divided by epsilon times h divided by delta t. And here epsilon cancel, and we get mu h divided by delta t. And this, of course, is the B we have over here. This equation deals with radiation, and in radiation we have electric field, and we have magnetic field, and we have a conversion factor to calculate between the electrical and the magnetic field. And this is the mu over here. And the same if we have h divided by delta z equals square root mu epsilon. And then we get 1 divided by square root mu epsilon times E divided by delta T, and then mu cancels, and we get epsilon E divided by delta T. And this is called D, but it's nothing but the electric field and the conversion factor to calculate from the magnetic field to the electric field. I have made a small paper about radiation, and it can be downloaded from my homepage. And we have covered the first chapters, symbols and formulas, fields from radiation, which is about transmission lines, and something about the capacitor, but that I will talk about in the next chapter. And then we have Maxwell's equations, and there I have started with the rotation of E and expanded E to the forward radiation and the backward radiation, and I have done the calculations, and at the end I reach dB dt. And I have done the same with the rotation of the magnetic field. So if there is no separate fields but always radiation. There is no electric field without a magnetic field because there are always radiation. Then the result is automatically what Maxwell's equations are telling us.